welcome back to SK1 Kids, and we are back again with something new and very special because now we are going to just do quantum mechanics. Since we just know that actually quantum mechanics is very complicated and very difficult, you can say tough topic, but still, and we are as well as doing the Newtonian mechanics, you can call classical mechanics, and we are just doing JEE and NEET syllabus. But with JEE and NEET syllabus, we are also going to do now quantum mechanics. And I would also like to say you that we are not going to do it in any kind of mathematical way, but we'll do it in a theoretical way, in a historical manner, according to the series of events that helped develop the quantum mechanics. We'll be doing it according to that in this playlist, and we'll be doing it in a total theoretical manner because the maths of quantum mechanics is what makes it complex. The maths of quantum mechanics is very complex. It is rather difficult to understand that, so we are going to do it in some kind of theoretical manner. And today is the first video, and the topic name is the reluctant revolutionary. I'd also like to say that what is the reason the topic was reluctant revolutionary, and the reason is all because of Max Planck. Max Planck, who helped to develop the quantum mechanics theory, you can call quantum theory, quantum physics as a whole. So Max Planck unwillingly developed it. In 1914 December, when he solved the black body problem and discovered about quantum, about the packets of energy that light emits. So basically in that, unwillingly he had done. That's why it is reluctant revolutionary. It's reluctant revolutionary. I'd also like to state a quote by Max Planck that briefly summarized of what I did can simply be described as an act of desperation. Okay, so this was just Max Planck's quote, and there are also other quotes by great scientists, and I would also like to quote one by Niels Bohr, that for those who first come across quantum theory and are not shocked, cannot possibly have understood it, because quantum theory is too complicated and it's very shocking kind. So we're just going to do here. I'd also like to say that Max Planck always stayed away with science matters. He always tried to stay away, but when he entered into arena, he did what? And he must do what he had to do. He also once told his student that my maxim is always this: consider every step carefully in advance, and if you then believe you can take the responsibility for it, let nothing stop you. So Planck was not a man to change his mind easily. We're just going to now begin the topic, and the topic begins with light rays, because quantum mechanics is much of light rays. And all heated objects, if hot enough, I'd like to say all objects, if hot enough, emit some kind of radiation and light. Just like if I just heat this board, so it will radiate some kind of radiation. How the sun is heated, so it radiates some kind of radiation, and we are able to see, and we call it fire. So later, if we consider over it carefully, just like a hot iron poker, if we heat it much and much, and when it becomes hot enough to radiate, first of all it will radiate some kind of light in the form of red color. First of all cherry red, then little more and more deep red, deep and deep, then orange, and like this continuing and continuing, it will finally radiate the light of bluish white color. So here, now if we leave it, when it starts radiating at bluish white color, if we leave it heating now, so it will again go to the reverse process, since according to the second law of thermodynamics, reverse process is never possible, but this is just about different matter. It will start going to the reverse process. It will be getting lower and lower, and again it will reach to the deep red, and then cherry red, dull red, and finally it will stop radiating. Of course it still radiates, but we are not able to sense it, and we are not able to see it. Finally, when it stops radiating even red color light, it is still some hot, so it radiates, we are not able to see it. And then finally in some more time it stops entirely radiating, and it is now cold enough to touch. So here we can just see that how any kind of object, if heated, can go through all the processes. Now turn comes of Sir Isaac Newton. In 1666, what happened? That the 23-year-old Sir Isaac Newton, a great physicist, very great physicist and mathematician, showed that actually even white light is woven of 7 different bands of color. And if you pass the white light through a prism, so you can get all the 7 different colors separately. And the 7 colors are red, orange, then yellow, and then continuing. After that you can get green, then blue, then indigo, and finally violet. So if you pass the sunlight or white light through a prism, you can just get all the 7 kinds of colors. But now, whether red and violet represented only the limits of the light spectrum visible to human eyes, or it represented the limits of the entire light spectrum that actually exists. So for this was just lately answered in the year of 1800, when the great physicist and astronomer whose name was William Herschel, he found, when he was trying to detect those kinds of lights, when he was trying to heat some kinds of objects and trying to detect what kind of light they emitted at all. So he used very accurate and very nice mercury thermometers, and to his surprise, when he put the object and when he finally got the objects, the materials, an inch past to the red light, he was surprised. It was very shocking. Then he got something called that the light was invisible now. He had found the invisible radiation. Still, the objects, materials were hot enough to radiate. They were very much hot, but the light was not looking. There was no light after all, but they were hot. So how was this possible? This only means something like that they are giving some kind of invisible radiation. And this he named as infrared radiation, because it is something like beyond the red radiation, beyond the red color spectrum of all of it, of the sun bands of white light, different colors. So here we can just see he discovered about the infrared radiation. And just now about infrared radiation it was discovered, and the human eyes were already able to see the visible light that we are able to see actually. But Herschel discovered that there is some kind of radiation called the infrared radiation, and its wavelength can be that high in the frequency, that low. We'll be dealing with all of that just soon later, so we do not need to make it more complex before we deal with the terms. So you can call, but the human eyes are not able to detect them after all. And lately in 1801, just after 1 year of the discovery of infrared radiation, the great another physicist, astronomer, you can just call, whose name was his name was Johann Nitrate. He discovered that silver nitrate actually darkens when exposed to light. Silver nitrate darkens when exposed to light. And this was some kind of shocking thing. Writer discovered that it darkens when it is exposed to light, when it is given some energy. So this is possible that there is other kind of light, other kind of radiation to the other end of the spectrum, and this was another to the beyond the violet spectrum. Okay, it was violet, and so you can call this the other ones as ultraviolet radiation. And in 1801 something was discovered known as ultraviolet radiation, and then we got something kinds of radiations that are of the visible light that we are able to see. We can just see it is something quite very little yellow, it is something kind here black, it is something kind here white, and you can call this by which mark it is written, the ink is black. We are able to look after it, we can just see all of it. So this is white, this is red, we are able to just see. But there is some kind of radiations we cannot see, and the one is infrared radiation, and to the other end of the spectrum of visible light is ultraviolet radiation. So we have just got the terms, and those 3 terms we'll be using a lot while discussing more and more quantum mechanics. But the turn of quantum mechanics doesn't begin right now, but we are developing, just like you can call some terms, we can say that we are developing our understanding, further understanding of quantum mechanics or physics. Now theory also you may just call it. Then I would also like to later say that Earlier, the potters in their kin had already known, okay, that whatever kind of material you have of any kind of body, if you have any kind of body, and it doesn't matter that what material the body is made up of, but if you'll give it some same kind of temperature, like for example, I have here one body, and here one body, 3 bodies, all made of different kinds of materials, and if you give all of them the same temperature, so they will radiate the same kinds of colors. Means it doesn't depend on the material of the body. It doesn't actually depend the material of the body, but whatever temperature you give it, it depends over only the temperature. What color will the radiation emit, or range and intensity basically. So here, but this wasn't proved mathematically after all. In 1859, this was the potters knew long before 1859, but that year was when Gustav Kirchhoff started his investigations over it. The great physicist started his investigations over it, and then he visualized a kind of body named as black body, and that was great kind of thing, because if there wasn't a black body after all, there wasn't the quantum mechanics, there wasn't any kind of, you may call this video, there wasn't this playlist. So you can just say that for trying to perform the investigations over this kind of object, over this kind of relation, he tried to develop the relation between that. Why does it after all happens? Why does it only depend on the temperature, but why the radiation, the color, intensity and range of the radiation does not depend on what material the black body is made up of? Or okay, we can just say body at this moment. We are not physicists at this moment to go at that level. So when we actually understand about black body, okay, we just get to black body then. Okay, so for this, Kirchhoff tried to develop an understanding of some kind of body named as black body. Now, what is black body? Is it a body that is black? Oh, from a certain point of view, you can just call a body that is black. Okay, that's fun. Okay, just like this ink. Is this ink a black body? Okay, that's hard to tell. Really hard to tell. I'd like to say that Kirchhoff supposed that a body that is a perfect absorber as well as a perfect emitter is said to be a black body. Okay, that seems little ridiculous. Of course it seems. A body that is perfect absorber and emits no radiation can be said as black body, but how Kirchhoff supposed after all that a body that is perfect absorber and as well as a perfect emitter is a black body? How is it possible? So I'd also like to say the concept was also understood by me a few days ago. You must have seen, I think my father also recorded some video when I just understood when I woke, and he also uploaded. So I'd also like to say that suppose a kind of body, Kirchhoff said that a kind of hollow sphere, you can call hollow container with in one of its wall there is some kind of tiny hole. And if this is the case, so according to Kirchhoff, what must happen is any radiation, whether that is visible or invisible, whether that is ultraviolet or infrared or to the visible light spectrum, that is entering in the body, that is entering in the hollow container, then it will be going as it enters, that this will be a kind of perfect absorber. Suppose all of radiation falling over it enters through the hole. So this is a perfect absorber. Perfectly it absorbs all the radiation. And then what is happening if it is going back and forth between the walls of the hollow container and is then completely absorbed there? What is happening? This is a perfect, not emitter. This is not a perfect emitter. Okay, then how do we call it perfect emitter? We just call it because still there is some radiation after. Still there is some radiation which you are not able to detect. You might have guessed at the moment, and if you haven't, so this comes out the infrared radiation from the black body. It means a perfect absorber which we already have understood. Even a black body which is taking all of the radiations falling on the black body. Later, suppose when heated, if it is heated enough, if the black body is heated enough to emit the infrared radiation to the other end of the visible light spectrum, it means it will be really emitting the infrared radiation. And if it emits the infrared radiation, it means we are not able to detect the radiation. Perhaps it will be just emitting some more radiation, perhaps that are visible to human eyes. But if it radiates the infrared radiation, our human eyes will be not able to detect the radiation, detect the rays, detect the light coming to our eyes. And when that happens, when we are not able to detect all of it, so we just say that there's no light coming in, still there is light coming in from there. There is coming light out from there, but we will say that there's no light coming out from there, and the body appears to be black. And the choice of name by Gustav Kirchhoff was apt, because it was really true. The body will be considered as a black body. Really, that was amazing concept. Even I was shocked. I shockingly still tell it, because as Niels Bohr, I would again say Niels Bohr said that for those who first come across quantum theory, who are not shocked when they first come across quantum theory, cannot possibly have understood it. And this is true. He truly spoke of it, because I really say I am even myself shocked a lot. Okay, so moving on. Later Kirchhoff, when he developed the concept of a black body, a perfect absorber as well as a perfect emitter, he said that there's infrared radiation coming out from there. So later what happened? Kirchhoff developed a new law, because now he had a black body not to guide him. He did not have experiments, because he could not really see about real black body. He could not really develop a real black body at the time. But he really developed the concept, and thought experiments are just all of physics. In physics, we just try thought experiments and more, and we just understand many concepts. Even the special theory of relativity, the general theory of relativity were all developed by the thought experiments led by Professor Albert Einstein. Whether that was for special theory of relativity, the fastest moving train supposed by him, or for general theory of relativity, the accelerating elevator in space and zero gravity, zero acceleration due to gravity. No earth there. Okay, perhaps there was earth, but it was negligible. Okay, so it was a thought experiment. Now Kirchhoff tried to develop a law for him. He tried to develop a law, and that law could actually explain whether the range and intensity coming out of the radiation from any kind of body made of any material does depend on the material of the body, or doesn't depend on the material. But to his surprise, Kirchhoff discovered the Kirchhoff's law, which we all know today, that actually the radiation emitted by a black body or any body doesn't depend on the material of the black body is made, but totally depends on the temperature of black body. Whether that will be infrared radiation, whether that will be red color, orange, yellow, green, that will be blue, or you can call indigo or violet, or that is ultraviolet radiation. It will depend on the temperature of the black body, and whatever material the black body is made up of, if they all the black bodies have the same temperature, all will be radiating at the same color, at the same range, and at the same intensity. And the law was said to be Kirchhoff's law. But still, how much energy? We just know that what color, at what temperature, but how much energy was radiated after all? We cannot go deeply inside it, because we aren't physicists as Einstein, Planck and Kirchhoff and all those you can call Dirac, the great physicists were. But we can just suppose that how much energy can be out there. Can we find a relationship between temperature, range, intensity and energy, and how much energy is radiated, in what quantity is it radiated? Can we find a relation? Now, this problem was a major problem. It was actually a huge problem. So, what Kirchhoff supposed, that now Kirchhoff and his colleagues began solving the problem. They tried to solve the problem, and the problem was a huge problem, and then this huge problem was said to be black body problem. I'm really sorry, the power was just gone, electricity. So here the problem came to be known as a black body problem. Okay, to find out what was the relationship between the energy of radiation, just energy coming out from a black body, and the range, intensity, temperature, radiation, after all these terms. So later the Colleagues and Kirchhoff himself said to work over this. They worked hard very much, but still they got success very much later. When Max Planck in 1900 turned out to be the right person at the right place at the right time, when he himself solved the black body problem, introducing the new term quantum. And this was a great thing because it was the birth of quantum mechanics after all, and that was very important because if there was no black body problem, so there was no solution of black body problem, and if there was no solution of black body problem, so there would exist a quantum, but we would not be able to find out the quantum, and that there wouldn't be so many and as many discoveries and inventions today in science and in our daily lives. I think that would be just enough for today, and we will also proceed to the next in our later videos, and then we'll discuss more over the black body problem and continue our topic of reluctant revolutionary in quantum mechanics. Hope you enjoyed today's video, and thanks to you all viewers for watching this video.